Hello students, welcome back. We completed section 1, the theory of derivatives and graphs. Now let's do some problems. Section 2 is devoted upon the graph problems, and section 3 is on calculation problems. Graph problems first. Alright, here's a nice problem. Answer the following questions regarding the original function f of x, while the graph of its derivative function f prime of x is given below. And then please stop the playback and read through the problems. Part A to Part C. Part A to Part E, all these. Alright, what did you find? They're all about original function f of x, but the graph of the original function is not here. You have to answer those questions from the graph of the derivative function f prime of x. Furthermore, do you notice that part A and part B go together, and part C and part D go together? Do you see those? If you don't, well, let me explain. Part A is talking about the increasing-decreasing nature of the original function, and part B is about critical points and their nature. Now let's go back to section 1. You see, they're all about this. Derivative is positive, then originally is increasing. Derivative is negative, then originally is decreasing. And then the derivative hits 0, then we have critical points. And then as for the critical points, they're all about the signs of first derivative. Now let's go to part C and part D. Intervals for concavity. And then inflection points. They're all about this one here. Concave up, concave down, and they're related to the signs of the second derivative or the increasing-decreasing nature of the first derivative. And then when the concavity changes, inflection points. So let's go back to this. The signs of first derivatives versus the signs of second derivatives. The graph of the second derivative function is not here, so you'll have to rely upon the increasing-decreasing nature of the first derivative. So these are different. Signs of first derivative, increasing-decreasing nature of the first derivative. They're different. So part A and part B are mainly about the same thing. Part C and part D are something different. And then let me copy and paste the conclusion here, the summary version here. And then let's answer the questions, part A and part B. Okay, let's begin. First, let's discuss a wrong solution. In that case, I shouldn't call it solution. Okay, attempt 1. And this is going to be a wrong solution. I see this kind of answer a lot, but if you do this, you're going to get automatic 0. So look at this graph. Graph decreases down, so negative infinity to negative 1. Excuse me, sorry about the typo. Decreasing in negative infinity to negative 1. Increasing in negative 1 to about positive 1.5. Yeah, about right here. And decreasing in about 1.5 to about 3. To infinity. I see this answer a lot. This kind of answer is very common, and I'm afraid If you do this, you're gonna get automatic 0. This graph is the graph of the derivative function. You answered completely about the derivative. This graph decreases from -infinity to -1, increases from -1 to 1.5, decreases from 1.5 to 3, and increases from 3 to infinity. Do you see that? Decreasing and then increasing, decreasing, and increasing. Associate that like this. So graph hits the edge, so assume the same pattern continues. So this is decreasing, and then this portion is also decreasing portion. And then from -1 to about 1.5, increasing, and then 3 to infinity and beyond, increasing. That's basically how you answered, but this is a graph of the derivative function. The problem is about the original function. So you just earned automatic 0. How do you get it right? Okay, here is attempt 2. No, let's put attempt 2 here. Correct solution, I'll say OK level. OK level solution. Let's look at this down here. I'm not interested in the concavity, so let's postpone that. Let's look at the first summary. I want increasing, decreasing nature of the original function. And those are associated to positive or negative of the derivative function. And the graph here is the graph of the derivative function. Now, derivative is positive. Well, this graph is derivative, so function value is the derivative value of the original function. So y-coordinate, function value is y-coordinate, remember? That's positive. That means the graph is above the x-axis. So above the x-axis here, below the x-axis here, above. So those are positive derivative, negative derivative, and then positive derivative like that. See that? Positive, increasing, negative, decreasing. Above the x-axis, original increases. Below the x-axis, original decreases. So you can write like this. Oops. Increasing in -infinity to -3. Decreasing in -1 to -3 to 0. You see, above the x-axis, below the x-axis, and increasing in 0 to infinity. It's basically like this. Increasing, and then decreasing, and then increasing. Those are associated to this distinction. Here, this portion is above the x-axis, so positive. This portion is above the x-axis, so positive again. But this portion is below the x-axis, so negative. So positive derivative increasing, negative derivative original decreases. Positive derivative, original is increasing using this table here. This is good, correct conclusion, but I'll still say this is an okay level solution, not the perfect solution, because where is the justification? To a certain degree there is if you put something like this, but still it's not perfect. Okay level with these kind of additional marking on the graph, okay, it is perfectly acceptable now. Still, there's a bit of a distance, especially if you just write like this and no further justification, then it's actually a bit incomplete. Okay, then, how can we make it right? Let's discuss the perfect solution. Perfect solution, and then in this case, let's put some space in between. Oh, this is not good. Okay, let's get the x-axis. And then let's put the critical points, or x-coordinate of the critical points. That's -3, that's 0, and that's +3. Do you see those? Critical point here, when the derivative hits 0, derivative hits 0 here, derivative hits 0 there. These are not critical points of the original function. Alright, the derivative value has to hit 0. The graph of the derivative function must hit the x-axis. Okay, alright. Now, how about the property of the derivative function? Less than -3, the graph is above the x-axis, so the derivative is positive. Between negative and 0, graph is below the x-axis, so derivative is negative. Between 0 and 3, positive. Greater than 3, again positive. They're all above the x-axis. Now, how about the behavior of the original function? Positive derivatives, so increasing in this interval. Negative derivative, so decreasing in this interval. Positive derivative, increasing. Positive derivative keeps on increasing. And this tells me the nature of the critical point. Increasing, decreasing. That change gives me the local maximum, capital M for maximum, and decreasing to increasing. This change gives me the local minimum. Small m, lowercase m, stand for the minimum, and increasing and keeps on increasing with a bit of a pause. That's actually an inflection point, neither maximum nor minimum. And this diagram completely answers this problem, along with the justification. And following these arrows, as a matter of fact, I can sketch the graph. Increasing, decreasing, increasing, keeps on increasing like this. Of course, this is not a perfect graph. This is just a sketch. Not expected to be accurate, but still, x equal to -3, x equal to 0, x is +3, and then just following the arrow. This is the perfect solution. Please practice this. Let's see, what did I do in my answer key here? I have the perfect solution here. -3, 0, +3. Those are the x-coordinates of the critical points. And then above, below, above, above. So positive, negative, positive, positive. That's for the first derivative function. And the original function is increasing, decreasing, increasing, increasing. So maximum, minimum, neither. Perfect. Practice this.